Tristan Linscott, and this is Physics 2211, Lab 3, Black Hole. The purpose of Part 1 of this lab is to utilize Newton's second law in gravitational forces. We will simulate the motion of a star orbiting a black hole whose mass we don't know, so we can then use these concepts to analyze the star's trajectory and calculate the mass of the black hole. For the second part of the lab, to further understand the effect of forces on an object's motion, we will simulate a spaceship navigating the gravitational forces of both a planet and a black hole. We will then calculate the initial velocity needed for the ship to fly close to the black hole without crashing. A small preview of my findings is that the mass ends up being 1.44315 e to the 34 kilograms, and the initial velocity ends up being negative 2 e to the 7th, 5 e to the 6th, 0 meters per second. Here's some main ideas and relevant fundamental principles. First, Newton's second law. Newton's second law, also known as the momentum principle, states that the net force on an object is equal to the change in momentum over the change in time. This law also gives us our velocity and position update formulas. Next is the components of the net force on an object. There are two: the parallel component, which affects the change in speed of an object, and the perpendicular component, which is related to the change in direction of an object. Adding these components together gives us our total net force. Last is Newton's law of gravitation, which gives us an equation relating the masses of two objects and their distance between them to the gravitational force on an object. It follows Newton's third law, so the forces from the objects on each other are equal and opposite. These free body diagrams can help us see the forces involved in the experiment. On the left, we see the forces in Part 1. We can see that there's a gravitational force on the star, our system. In Part 2, shown on the right, we can see that there are many gravitational forces at play. Here, our system is a spaceship and planet, and we use these forces to find the initial velocity. Part 1 of the lab. First, we must establish our initial conditions: the gravitational constant, the mass of the star, and our change in time. Then, as seen on the right in the code, we inputted the important equations mentioned previously to calculate net force, its components, and the mass of the black hole. In the bottom left, we can see how we continue to iterate through this loop so we can calculate the average mass of the black hole by adding the mass after each calculation. Here are the results from Part 1. As seen, we calculated the mass of the black hole as 1.44315 e to the 34 kilograms. This is the average of all of our mass calculations after iteration. The star follows an elliptical orbit, and the gravitational force is greatest when the star is closest to the black hole and smallest when it's the farthest away from the black hole. This causes a change in velocity when it is closer to the black hole. Possible sources of error are the fact that after each iteration we rounded the result, which could lead to less exact answers. For Part 2 of this lab, we once again had to establish our initial conditions. This time we used the mass of the black hole we calculated in Part 1. We don't know the initial velocity, which we will calculate by using the Fnet of the ship from both the planet and the black hole. We will then add them together for total Fnet, which we will then use our velocity and position update formulas and iterate until we find the initial speed needed for the ship to escape the black hole. To find these forces from the planet and the black hole, we need the distance between them and all of their masses. For our results, we found that the initial velocity of the spaceship must be negative 2 e to the 7th, 5 e to the 6th, 0 meters per second. As seen, the spaceship is the bent magenta line, which shows it traveling very close to the black hole before shooting away. The cyan line is the planet, showing the circular orbit. Because our initial velocity is negative in the x direction, this means it's moving to the left. Once again, once it gets close to the black hole, it starts to speed up due to it experiencing the largest magnitude of gravitational force. Possible sources of error could be that the mass we used for our black hole was an average we calculated and could not be entirely correct. Additional questions. For number 1, we were asked to discuss the difference between the parallel and perpendicular components of net force and change in momentum. These values are actually equal, but the net force cannot be calculated without the mass of both the star and black hole. The components of change in momentum, however, can be calculated using information about position, velocity, and momentum. For number 2, we were asked to calculate what initial velocity our spaceship needed to have in order to enter an orbit around the black hole. To do this, we would need to increase the initial velocity in the y direction and decrease the initial velocity in the x direction. This new velocity, calculated after trial and error with our code, is negative 2 e to the 6th, 1 e to the 7th, 0 meters per second. Thank you.